Hi, this is Srirag Ramadagu. In this video, I'm going to cover some of the basics on support vector machines, which is commonly called as SVMs. So, SVM is a supervised machine learning algorithm that is capable of performing linear or nonlinear classification, regression, and even outlier detections. So, its main objective is to find a hyperplane in an n-dimensional space that can classify different data points. So here n-dimensional space, which means uh, so n is the number of you know classes that we are using. So number of features, and so looking at this graph, you can see these two different classes of points are being divided by different lines, and the optimal hyperplane is said to be which has a maximum margin. So let's see what are generally what is a support vector. So from the graph we can see that there are two classes of points. So one class I have represented it as plus and other as minus. Now you can see the closest points are being divided. You can see a hyperplane, and the point where the hyperplane is there is present is being influenced by some of the points, of the closest points. And uh, if so all the points that have influence on the hyperplane, they are called as support vectors. So uh, on the area in the area if the points are in such an area where those points doesn't have any influence on this hyperplane, so whenever there is new additional data adding to our model, and if that data is being added to that, if those points are being added in this area, then there is no effect on this hyperplane. So all those points that has influence on the hyperparameter are said to be support vectors. And let's get to what is hard margin classification. So when we strictly impose that all the instances be on the street and on the right side, it is called hard margin classification. In simple words, I can say that, so if suppose there are two classes, class A and class B, and all the points in class A and all the points in class B are to be exactly classified. If one point from class A is in the classified as a class B, then that's not hard margin. You are supposed to classify each and every point. So that is what you call as a hard margin classification. So, and the issues with it, obviously it's more sensitive to outliers, and it works only on linearly separable data. So what is soft margin classification? It's exactly opposite to what hard margin classification is. So you are going to let some of the points be on the other side when classified. So you know um, what kind of model do we need? So we need a good balanced a model which is balanced between keeping the streets as large as possible, that is the margin of the hyperplane, as well as limiting the margin violation. So how do we control this balance? We can control this balance using regularization method. So here we are going to use the hyperparameter c, which we are going to tweak it, and based on those values we are going to determine if it's a hard classification or a soft margin classification. So using this c hyperparameter, the lower the value of the c, then the street, I mean the margin of the hyperparameter is wider and margin violation is more. So when you increase the value of c, the street gets narrower and the margin violation gets fewer. Coming to the tuning parameters, of course, the regularization that we talked about in the previous slide comes under tuning parameters, and then now kernel. So if suppose the data is in this way, as shown in the first figure, so you have two classes of data points. So first class is in the middle near the origin, and all the rest of the data is around it. Now you are supposed to classify them. So of course these are not linearly separable, and so we can't draw a line and separate these two classes. Here we are going to consider, we can use transformations on this. We will add another plane, z-axis. So I would say it's a distance from the origin to those points, and I'll transform it to zy plane as shown in the second figure. Now in the second figure we can see that this data points can be classified with a single straight line. So these are linearly separable. So drawing a line parallel to y-axis. So when I transform this back to a two-dimensional xy plane, the result will be a circle, x squared plus y squared. So this is possible by using a dot product of the vectors of the distance vectors. Now uh, kernel makes it easy to do these transformations. uh, so that's how kernel is used. And now coming to gamma. So gamma defines how far the influence reaches the points from hyperparameters. So as we were discussing about support vectors, and we talked about the influence of the points from the hyperplane. Now the higher the gamma, the near points are only considered here. So if I keep the gamma variable high, the only the points that are near to the hyperplane, or I would say the margin, are only considered. And if the gamma value is low, the distant far away points are also considered here. So I would say uh, it mostly depends on the data points, uh, when the gamma values are to be changed. And now coming to the margin. So margin is separation of the line to the closest class point. So you can see from in the first figure, the two classes are being classified by the hyperplane with an equidistant from both sides. So this is a good margin. And the second figure, it's not equidistant; it's more inclined to the minus class. So this is a bad margin. Now let's implement SVM classification on a dataset using Python. So for this, I'm using make moons dataset, which I have imported from sklearns. So you can see here, uh, I have taken 100 samples with noise of 0.15. So I just chose random status 42. So every time I do the same thing, I can get the same data. Then I just plotted it just to see how the data is. So from the plot we can see that there are two moon shaped uh, data points. So there are two different classes of data points which are moon shaped. So we are supposed to classify these. Obviously we can't use linear classification here, so we are supposed to use kernels or polynomial features to classify these two classes. So here I have used sklearn preprocessing polynomial features. So I have imported polynomial features from sklearn preprocessing. I have set a pipeline with polynomial features and SVM classification. So you can see the C value is 10 and loss is equal to hinge, and I have kept this random state as 42 in same. So after this I wanted to check the classification output. So how did I do that? I have defined a plot prediction function that would take in the classifier model and axis values, and I have used the line space functions to define the line space, and then mesh grid function to define the mesh grids as you can see in the picture. Then The classifier dot predict will give us the predict values, and so I have called the predict the graph, I mean plot predictions function, and I have sent our polynomial SVM classifier model with the access values. So as you can see from the picture, the two classes are being separated with this polynomial curve using this SVM classifier. Of course, we can see there is one triangle in the other classifier in the other class, and you can see here the square coming out. So we can try using uh, instead of soft margin, I can use hard margin and try to cover these. But when you try to cover these, when we try more for the precision here, this model will be unstable in the future when there are new data coming up. So here is an SVM model. Thank you for this.